the right cancellation law is true. Why is the right cancellation law true? For the right cancellation law, we will need something like this, na? X dot z is equal to y dot z. Then that should imply x is equal to y. If this happens for all choices of x, y and z, then the right cancellation law is true. What are the products that we have here? See, a dot a and a dot b are equal to a, b dot a and b dot b are equal to b. So do we have a situation where the second product, where the second factor in both the products are equal and the products are also equal? Here the second factor is a, however the one where the second factor is a again is this one, but a dot a and b dot a are not equal. One of them is a and the other is b. If the second factor is taken to be b, then this is one product, a dot b, this is the other. They are also not equal. So the hypothesis is not there at all, or the hypothesis is false. So the conclusion is vacuously true. This implication is vacuously true. So that's why the right cancellation law is, we can write, is vacuously true. Similarly, the right cancellation law. Now we come to the second operation, start. Now in this case, in case of start, the right cancellation law is not true for star. Can we see why that is not true? Yes, because a star b is equal to b star b, but we cannot cancel b from both sides. It's on the right side of both the products because a and b are different. But the left cancellation law, in this case the left cancellation law is vacuously true. Okay, so we have got at least a system, actually two systems, where in one of them the right cancellation law holds but not the left, and in the other the left cancellation law holds but not the right. In both the cases, G is not a group. Note that G is not a group under either of the operations. Why? What is the reason? Because A dot B is not equal to B dot A, and A star B is not equal to B star A. A dot B and B dot A are different, and so are A star B and B star A. And what problem does that make? Here we encountered the problem that if these systems are groups, if any one of them is a group, it has to be abelian. However, we can see that the operations we have defined are not commutative, and that is because any group of order 2 is abelian. Recall that while solving exercise 9, we have said that not only are groups of order 3, 4 and 5 abelian, but groups of order 1 and 2 are also abelian. So since here that possibility is not there, so these systems cannot be groups. So we see that finiteness, closure property, associativity and one of the cancellation laws are not sufficient for having a group. We need all these things, and finiteness is also needed. What happens when finiteness is not there is seen in the next exercise, whose solution is very small. Prove that in exercise 14, infinite examples exist. Satisfying the conditions which are not groups. It's very easy to come up with such an example where we have a non-empty set which is infinite. There is an operation with respect to which the set is closed. The operation is associative and the cancellation laws are also true, but the system is not a group. Consider the set of all positive integers under multiplication of integers. If we multiply two positive integers, we are going to get a positive integer. So the set is closed. Multiplication of positive integers is an associative operation. If you have something like this, if you have say three integers I, j and k, where they are all positive, and you have ij equal to ik, then since I is positive, it's non-zero, so you can cancel I from both sides to have j equal to k. So the left cancellation law is true, and since the operation is commutative, the right cancellation law is also true. So all the conditions are true of exercise 14. The only thing that is different is that the set is infinite, and we know that this is not a group. Why is it not a group? You see, closure property is there, associativity is there. In fact, identity element is also there. 1 is an identity element. However, inverses do not exist. The only element whose inverse exists in the set is 1, because 1 times 1 is 1. However, every other positive integer fails to have an inverse. 2, 3, these don't have inverses in the system. For the inverses to exist, you have to jump to the system of rational numbers. So you are getting outside of the set. So this is not a group. So this is the solution.